Alright, hello class. So today in this video we're going to be talking about triple integrals, and a lot of what this section's all about you've really done the heavy lifting for. So all we're really doing is adding another integral. The actual calculation of them, it is the same, right? So mechanically they're the same, we just have a z integral and on top of the x and the y. However, the big points here are going to be, first of all, what are these things? All right, so what are they? And the other big one is how to set them up, right? It tends to be the tricky part in all of this. Okay, so I'm hoping to focus mainly on that, on the setup and on, what they are, because typically once you get these set up, the integral part just kind of follows along. Okay, so let's start with what these are, and I think that's the trickier part, because you might not think there's much further to go from volume, right? Because we've already done volume. So let's see what we can. Okay, so just to recap some of these things, of course we already know. For the single integrals, what that gives us is the area, right, with the idea that we build that up from rectangles, right, with base delta x, and the area is approximated, right, by the sum of heights, which we get, right, from f itself, and times the length of the base, right? So delta x by f. So that ends up giving us the definite integral from a to b of f of x dx. So what ends up happening here is this is the height, and this is the base. Okay, so what ends up happening is this delta x, the bases shrink down to 0, while the number of rectangles we get increase to infinity. So we get that typical 0 times infinity case, which, especially in the case of integrals, actually comes out to be finite. All right, so then we move to double integrals, which kind of followed from the same idea. So if we had, say, a region here on the xy plane, okay, we could map that up to some height given to us by f of xy. Okay, so once again, what ended up happening is we would take delta x and a delta y, and together they would be a delta a, and then we'd create a height from the function itself. And, we didn't get too detailed here, but the height comes from f. So what we end up getting is that the volume, right, of this solid is approximately the sum, and it's going to be a double sum of the heights, right, times the base. Right, so this, once again, here's the height, and this is, whoops, that should be a D, sorry. This is dA. That is the area of the base. All right, and that's always a quick way to get volume. If you're just adding height to something, you just multiply by that height. That's essentially what's going on here. So this comes out to be the double integral, okay, over R of f of xy dA. And I totally jumped the gun here. I was right the first time. That's delta A. Okay, so once again, the heights come from F, and the area of the bases come from dA. Okay, so then the question is, well, how do we take this further, right? There's not much that it seems like that we could do. And so let's talk about that. So how do we jump from this to triple integrals? All right, so what are triple integrals? Okay, so to imagine what triple integrals are, imagine a solid S. In 3 space. Okay, so if we make our coordinate system here, suppose we have some sort of solid. Who knows what it looks like? Okay, so suppose this is our solid. Okay, so let's say that this is our S. Okay, now imagine that at each point within S, there is a function that gives us some value. Okay, so what I mean by that is within S, there's tons of points inside of S. Right? And in each one, suppose that f of x, y, z gives us some information. Right? And this is some information within S. So what do I mean by information? Well, the two things I like to think about are temperature. Right? That's a pretty basic one, that within, say, if this is like some, I don't know, piece of jello or some sort of object, at each point within the object, it's going to have a certain temperature, and the temperature over here won't necessarily be the same temperature over here. You can also think about, and this is the really common one, and the one we'll be talking about the most, is density. Suppose that F gives us the density at each point within the object, and objects you can think of have different densities throughout. So you could maybe think of like a planet, right? A planet is way denser on the inside, like near the core, than it is on the outside. Okay? So I'll just say, for example, e.g. here, imagine F gives the density. All right, and then from here, what we do, so if we imagine that F is the density of S at each point x, y, z in S, then what we do is, like we did before, by either chopping it into boxes or chopping it into rectangles, we chop S into a bunch of little cubes, right? Little cubes that are delta x by delta y by delta z. Okay, and each one of these little cubes, I'll zoom in on it here. Okay, here's a delta x, delta y, and delta z, and all together, right, this is going to be a delta v, the volume. And so what we do is we pick a point within this cube and pick an f. It could be at this corner, it could be at this corner, it could be right in the middle. That part doesn't really matter, but we could call that the f of x sub k, y sub j, and z sub I. Okay? So, and then just take that as the density of this little cube. All right, so we wrote a little bit of this down. We're going to split S into n by n by n. So I'm just assuming that it's the same number in each variable, but it could be n sub x, n sub y, n sub z. That part doesn't really matter that much. But we're going to calculate the mass of each cube. Right, so the mass of this cube, all right, so I'll call that kji, right, is going to be the density, which is F, right, times the volume of the cube, right? Mass is density times the volume, and that in this case it's going to be delta V. So here, this gives us the density, this gives us the volume. Okay, so the total mass of S can be approximated by the triple sum, all right, of the volume, or excuse me, of the mass of the cubes. Okay, right, which is this guy here, which is essentially an integral. So we'll get equality as delta V goes to 0, as the number of rectangles, or not rectangles, but as the number of boxes goes to infinity. Okay, we get equality, which will be the triple integral over S of f of x, y, z dv. Okay, so just like before, this is going to be f will be our density function, and dv represents the volume. Okay, now there are other ways to do this. Like I mentioned, heat. The only thing you have to sort of worry about with like the temperature of an object is saying the total temperature doesn't really make much sense. So what you would really look at is the average temperature. So you would you could take the triple integral and then just divide by the volume of S. I don't think we'll be really looking at that, but that is another application of this in physics. Okay, so this is what the triple integral is, right? The F is our density function, dV is our volume, and the S itself, the limits of integration, describe S. Okay, so just like up here, I think it's on the same page, yeah. Here, the limits of integration describe the region R on the x-axis. Here, the limits of integration represent this length of the base, the total base, right? Much in the same way for a triple integral, S, those limits of integration describe what S is. Okay, so how do we set these up in practice? Okay, so if f of x, y, z gives the density of S at the point x, y, z within S, okay, then the mass of S is this triple integral. Now, how we set this up, Well, there are a myriad of different ways to do this. Here's the suggested way that I like to set things up when possible. Okay, what I like to do is, if possible, okay, set this up with a x integral on the very outside. So say x going from a to b. All right. Then the middle integral, if possible, let y go from what I'll call the bottom of R to the top of R. And, well, what's R? Well, we're going to set this up in the same way that we did before. So R is essentially how S is behaving with respect to X and Y. Okay, so I'll explain this a little better later, but so we can think of this as the bottom of our region. And the reason I'm writing it this way is because we do it exactly like we did with double integrals. So I'm trying to keep the same notation, the same names here. And then I want the inside integral to be z's. So I want it to be z. All right, z goes from the base of S to the, I don't want to use the top again. So I could say, instead of that, maybe the roof of S. Okay, so this is basically the bottom to top in terms of the z-axis. Okay, then your f of x, y, z, and then, of course, the order here is dz, dy, dx. Now again, this isn't the only way to set this up, right? And in some cases, this isn't going to work. However, when possible, this is, I think, the best way to go about doing it. Okay, so let me show you what I mean through an example. So let's evaluate the triple integral over d of 2x dv, where d is the region bounded by the plane 2x plus 3y plus c equals 6 in the first octant. Okay, remember the first octant, this is when x, y, and z are all positive. Okay, so it's kind of like the first quadrant, but again, in 3 space we have octants. Okay, so we want to evaluate this triple integral where d is the region bounded by this plane only in the first octant, and so we need to figure out what this shape looks like. Okay, so I found the quickest way to do this, if I want to graph, is, well, we can find the traces, but I like to find the points. Okay, I like to find, basically, I like to set x and y equal to 0, which then gives me z equals 6. So that tells me that I have the point 0, 0, 6. Then I let x and z equal 0, okay, which gives us 3y equals 6. So we'll have the point 0, 2, 0. And then I'll set y and z equal to 0, which will then give us that 2x is equal to 6, giving us the point 3, 0, 0. So these are actually the z-intercept, the y-intercept, and the x-intercept of the plane. Okay, and when I have those pieces put together, we can actually get a pretty good idea of what this plane looks like. And you know, we did do this a bit in the lesson where we were talking about planes, but one, to just refresh your memory, but two, to show you don't have to do the full lines, you can just find the points and put them together. All right, so here we have basically this representation of the plane in the first quadrant. We're bounded by this plane, and we're basically making this sort of prism here. Okay, so this is what represents our object, our solid S. All right, and if you wanted to just graph it by hand, you could. This would be 0, 0, 6. This would be 3, 0, 0, and 0, 2, 0 would be here. Okay, so we make a sort of prismy shape. Okay, so here is our S. Now, the trick is actually how do we represent this as limits of integration? Okay, and so that is where we start developing what's happening in terms of X and Y. All right, so here is the plane that we were given, which was, show it again, 2x plus 3y plus z equals 6. And actually, I'm going to write this like z equals 6 minus 2x minus 3y. Okay? All right, so what I want to do is show what's happening in terms of X and Y. Okay, so when we look at the different values of X and Y in relation to this solid, all right, we want to find the, so how we do this is we want to find the, say, the X value that would give us a good representation of the maximum that X or Y could ever go. And if we look straight down, we see this triangle here. Okay, so this would be the x-axis, this would be the y-axis, or was that the other way around? Yeah, this would be the y-axis, this would be the x-axis, and we can see that if we let, in terms of X and Y, it take up this whole triangle, we will account for everything, right? There won't be any X's and Y's that aren't found within this main triangle, and that main triangle lives on the XY plane. Okay, so I'm going to write some of this and show you how we... All right, so all possible X and Y values live within this triangle, and that triangle is on the XY plane. Okay, so that means we're going to look at, well, the XY plane. So we will look at the XY plane. Okay, in other words, that's when z is equal to 0. All right, so let's do that. When z is equal to 0, we'll use this version of it. When z is equal to 0, we get 2x plus 3y is equal to 6. All right, and then if I move the x around and divide by 3, we'll get y is equal to 2 minus 2/3 x. Okay, so we get a line on the XY plane, which is essentially what I hope we should have expected, because what we ended up with was a triangle when we were looking at the XY plane. So what we're talking about here is a line, right? So this line has y-intercept 2, and it's going to have x-intercept 3. Right, so it looks something like this. Right, so here's the line, y equals 2 minus 2/3 x. Okay, well, in order to get the whole triangle, we're going to have to go from the base here, which is y equals 0, up to y equals 2 minus 2/3 x. Right? That's going to give us the whole triangle, and this is what I meant by saying that we set up those outer integrals just like we do when we're talking about r, right? For double integrals. So this is our bottom, this is our top, and our x's range from 0 to 3. Okay, so this gives us the inner limits. Okay, the inner limits are x goes from 0 to 3, and y goes from 0, which is the bottom, to the 2 minus 2/3 x, which is the top. Okay, so now we're almost done. All we've got to do is find the limits in z. Well, to find the limits in z, they're practically given to us here, okay? Because if we say look at this, let me go back to the 3D graph where I can show it from different angles. Okay, so here we go. What I've done is shown what this, to match it how we have it in our graph and our work. So we see basically the top of this prism is here in purple, while the base is in red. So the base, if we're talking about in terms of z, that's when z is equal to 0. Okay, so the base is z equals 0. And if I map up from the base up to, say, the top is z equals, and maybe I shouldn't use top here, I should probably call it the cap. Yeah, the cap or the roof, okay, is the plane itself. Right, because if we were to draw a line from, say, perpendicular to the xy plane here, base to height would go from, say, the red triangle, which is z equals 0, to the plane itself. All right, to explain what I'm talking about here, I've drawn a line from the base to the cap of the object, right? And so if you were to draw a line just straight through the object, just like in the 2D regions, we're treating this the same way, and the base is the red triangle, while the cap or the roof or the ceiling is this purple part of the plane. Okay, so this is going to be the lower limit of z, and this is going to be the upper limit of z. Okay, and when we put this all together, we're going to have the following limits. All right, we're going to have the limits x going from 0 to 3. Okay, y going from 0 to 2 minus 2/3 x. Okay, and z going from 0 to 6 minus 2x minus 3y. Okay, and then the integrand, I believe, was 2x, and then we'll have dz, dy, dx. Okay, now I do want to stress that this is not the only way to set this up. However, in my experience, this is the nicest way, if you can get away with it. Most cases you can. Okay, that's, you know, most cases you'll be able to do this. Okay, so I don't, this integral shouldn't be that difficult to crank through. Okay, in my notes, I got that this was equal to 9. So how about you give that a shot and see if you get out 9 when you crank all this through. I really want to focus on the setup in these examples. Okay, so in the interest of just looking at how we set these up, because again, that's always the trickiest part, here's an example where that's all we're going to do. We're going to set up this integral, triple integral over s of f of x, y, z dv, where s is the solid bounded by the cylinder, z equals 4 minus y squared, and the planes, z equals 3y, x equals 0, x equals 2, and y equals 0. Okay. This is going to be tricky to set up. It's going to be tricky to visualize. However, there's a way that we can actually do this if we just start piecing it together. So if we're talking about the cylinder, z equals 4 minus y squared, well, that, if we were to graph that on, let's say, the yz axis, 4 minus y squared is going to look like this. Right, so this is on the zy axis, but remember what a cylinder does is that no matter what x is, whoops, let's try that again. No matter what x is, we're going to get this same parabola out. Okay, so it's going to look something like this. Okay, so that's that cylinder. Then if we think about this first plane, z equals 3y, well, that's actually a very similar idea. If we just graph that on the yz plane, z equals 3y is going to be, well, it's going to be a line, right? And since, like, let me make that a little steeper. This is a little more obvious what's going on. Here we go. There's z equals 3y. So if I put the z-axis in now, we're going to have this same line throughout. So this is actually another type of cylinder, really, but just in terms of a line. Okay. Okay, so to show that on an actual graphing software, here is that cylinder, z equals 4 minus y squared, and if we look at it on the, let me change the color of that, there we go. If we look at it on the yz axis, we see that it's just a parabola, and then we're basically extending it out along the x-axis. Okay, and now if we look at this straight on again, there's the line z equals 3y, and here's the plane that corresponds with that. Okay, so you can kind of see where they intersect here on the yz axis, and that's essentially what we're creating here. Okay, so all right, so here is what we got on the yz axis. Now note, this right now has, I didn't need to look at the 3D software at all to get this part. Okay, this part I was able to get just from foreknowledge. Okay, now the next pieces I'm going to set up are these planes, x equals 0, x equals 2, and y equals 0. And those I'm going to look at on the xy plane. Right? So on the xy plane, right, we can actually think of these as sort of cylinder-ish as well. X equals 0, right, is going to be this line here. X equals, I believe it was 2. Let me just double check on that. Yep. X equals 2 will be this vertical line. And then y equals 0 is, of course, this horizontal line. Okay. Let's put those on the graph, but what I want to say is that essentially, if we're only looking at, let's start here, y equals 0, the plane y equals 0 on the YZ axis is going to look like this. Right? This is, if we're just on the axis, the line y equals 0, and it's going to trace out just like this one did. Okay, back to our graph. If we're looking at the YZ axis, here's the line y equals 0. Whoops, here it is. The line y equals 0. Right, coming up through there. And then if we turn that into a plane, we get that. So what we're essentially talking about is this little shape here. Okay, so essentially, we're bounded here, and notice that I didn't even look. Well, I could have gotten this without looking at the 3D space. And now we're just going to restrict x from 0 to 2, and that's actually going to give us the full shape. Alright, so as you can see here, I've cleaned this up a little bit. This was the bounded region we got. And then if I take the z-axis out, and then I put this region, say, here, right, and then piece it together, we sort of get an idea of what this object looks like. Okay, and we know that x is only going between 0 and 2. So we've sort of created a wedge shape. Okay, so I'm not going to graph these planes in x, but I just know that if this is the x-axis, we're taking this shape here and moving it out this way. Okay, so to give a little look on the on our surface here, we're just restricting this to this piece here. Okay, so let's see if we can get a better look at that. All right, so here we have restricted these surfaces down to really just what we're looking at. I've only done it to this shape. Now keep in mind, I wasn't able to put this flat piece in for whatever reason. Okay, and then we'll just restrict it to the z, and that's going to give us our limits. Alright, so here I've reduced this down to this little guy here, and we can see we've basically created a wedge when we put all this together. Okay, so here's how we're going to do our limits. Alright, so we're going to start with the z limits. And so if we look back up here, for our z limits, we're going to do base to the roof. Okay, so the base is this line, which is z equals 3y, and the roof is this z equals 4 minus y squared. Okay, so that's now going to be our limits. Our limits go from 3y to 4 minus y squared. Okay. Now we need to talk about the y limits. All right, and so the y limits, one of them is actually given to us. And how we go about this is from here. We know that y equals 0 is one of our limits. The other one we do the same way we did back in double integrals, is we want to see how far out y goes. So y is going from 0 to something here, and we just need to see where these two intersect. Okay, so we'll set them equal to one another. So we'll get 4 minus y squared is equal to 3y. Move some things around. We get 0 is equal to y squared plus 3y minus 4. And this should factor into a y, what will that be, plus 4 times y minus 1. So we get y is equal to negative 4 and 1, and so it's going to be 1. Okay. So in this case, the y limits are constant, going from 0 to 1, and the x limits, as we've already established here, x is just going from 0 to 2. Okay, now if we go back here on the xy plane and graph the y we just found here, the y equals 1, that would be right here. Okay, what this has given us is a rectangle which will cover everything, right? And so if we look back on the graph and look at it from the top, we see we have a 2 by 1 rectangle. And that's exactly what we're showing here. And that's what's happening on the xy plane, giving us everything we need. Okay? All right, with the time left, let's do another example. Okay, so let's set up this triple integral over S, where S is the solid bounded by the cylinder, y equals x squared plus 1, and the planes y equals 2, z equals 0, and 9y minus 3z equals 0. Okay? So to start out, I'm just going to start putting pieces together. So I'm not even going to look at the 3D graph until I've got an idea of what this thing looks like. Okay, so to start with, this cylinder, y equals x squared plus 1, well, we can graph that on the xy plane. That looks like this. All right, so here's y equals x squared plus 1, and since there's no z involved, for every z we're going to get this sort of guy here. Okay, so if I put this on the R3 space, right, this is x, y, we'd have something like this. If this is what the parabola looks like on the xy plane, we're basically graphing it upwards. Okay, something like that. All right, so there's that cylinder, y equals x squared plus 1. And now these planes, y equals 2, z equals 0, and this, well, these just give us essentially our next limits in y. So y equals 2, well, here's 1, y equals 2 will be here. Oops. Okay, so if we're bounding by these two, then we're basically looking over this purple guy here. So we could actually say, let's say it's this. Okay. So this actually gives us, let me try that again, sort of a idea of what we're piecing together here when we bound these. So we're taking this purple region and stacking it on top of each other. Okay? All right, so there's this cylinder and this plane, y equals 2, and then z equals 0. Well, z equals 0, that's the xy plane. Okay, so that means we're starting here. So let's try that, a different color arrow there. All right, so here's z equals 0. Now we just need to see where the top is, or if this is the top, where the bottom is, and then we're going to get that from this plane, right? So this plane, the 9y minus 3z equals 0, well, if we move these things around, we'll get 9y is equal to 3z, so we get 3y is equal to z. Well, that looks and sounds familiar, right? That's just a line. Okay. Interesting. So we have a line here, and then what we're essentially doing is cutting this guy here by that line. Okay. Okay, that looks very odd. All right, so if I look at it on the side, so let's say that this is the y-axis. So say, well, of course it is, because this is the YZ axis. Well, I know y only goes from 1 to 2. Right now it's going from this function here, but basically the y is trapped always between 1 and 2. So we're basically creating a wedge like this, but then if we also incorporate the x-axis coming out this way, we're basically creating our parabolas like this. Okay, so we're essentially creating some sort of wedge type shape. And so now what I'll say is that I will show you what this looks like on a 3D graph. However, what I want to also show you is that it doesn't really matter because we can still set up the limits. Right? So the limits in z, well, z is going from, we know it starts at 0 and then it pops up to this line. Right? So it's going from z equals 0 to z equals 3y. Okay. So this is the base, this is the cap. I don't even need to know what this whole thing looks like in 3 space to get this. I just graphed everything I possibly could together. Okay. Then we're going to look at the y. Well, the y, well, we know, now we can talk about this in terms of bottom and top. The bottom is the y equals x squared plus 1, and the top is y equals 2. Okay? And then for the x limits, well, all that's left to do here is see where these intersect. Okay, so 2 is equal to x squared plus 1. Well, we move the 1 over, and that tells us that x is equal to plus or minus 1. So the limits in the x variable are -1 to 1. Okay. And so we'll have dz, dy, dx. And there we go. Now notice, I still don't really know exactly what this looks like altogether, but it didn't really matter. I can still set this up despite that. Okay, so just to show the the graphing software is having trouble putting this all together, but here's essentially what we're looking at. We have this guy, which we're mapping upwards, and we're stopping it here, and then we're essentially just slicing it, okay, to make a bit of a I think of it as like a doorstop, so let's see if I can draw a cleaner graph here. So it's sort of like something like this, okay, when it's all said and done. Okay, so hopefully all this is enough to help you on the homework. Again, you're not really going to, I think, really wrap your head around this until you actually start trying to piece these together. However, once you get them set up, the integral just rolls like it usually does. All right, so I will catch you all on the next one. Cheers.